All right, if you remember in the last time we were going through chapter 14, we were looking at gas laws, right? Those are those mathematical relationships that show how different variables in gases are related to each other. How is pressure related to volume? How is volume related to temperature? How is pressure related to temperature? Well, we looked at three laws the last time. We looked at Boyle's law, we looked at Charles' law, we looked at Gay-Lussac's law. If you combine all three of those, we can come up with what we call the combined gas law. Okay? So let's look at those three laws again. So we had Boyle's law, which was P1 times V1 equals P2 times V2. Right? So we were looking at the relationship between pressure and volume. Right? Remember that pressure and volume change inversely to each other. So it means as pressure goes up, volume goes down. Or as volume goes up, pressure goes down. Now that's assuming that the temperature didn't change. Then we could look at, this was Gay-Lussac's law, which is pressure and temperature. So P1 over T1 equals P2 over T2. That's assuming that your volume doesn't change. So this container would have to be one of those containers where the volume couldn't change. Or we could look at Charles' law, which was V1 over T1 equals V2 over T2. So volume and temperature. But the pressure didn't change. Now, what if we had a container that didn't have temperature constant or volume constant or pressure constant? What if all three of these things could change? Well, then we'll have to look at all of them together. So we can combine all of these gas laws into one, which would look like this. Right? P1 times V1 divided by T1 equals P2 times V2 divided by T2. So this is the combined gas law, and it really is sort of a replacement for all three of those. Instead of having to learn three separate gas laws, we can combine them into one and use them whenever we want to. Let's say that we only need pressure and volume. Then just ignore the T's, right? If you ignore the T's, this turns into P1 times V1 equals P2 times V2. What if we had a situation where the pressure wasn't changing? Then just ignore the P's. And now you have V1 over T1 equals V2 over T2, and so on and so forth. We can ignore anything we want to if we have a problem that doesn't need all three. But if we do have a problem that needs all three, now we have a gas law that can use that. All right, so let's try this out. This time what I want you guys to do is I want you to read this problem here, and I want you to go through and label which one is P1, V1, T1, P2, V2, T2, whatever you know. I want you to label it and write it as knowns and unknowns. So go ahead and pause the video for a minute and do that on your paper. All right. So you should have paused by now and written out your knowns and your unknowns. So let's go through this. It says a gas at 155 kilopascals. Kilopascals, that sounds like a pressure. So this must be P1, right? And 25 degrees Celsius. Well, that's a temperature, so that must be T1. Has an initial volume of 1 liter. Well, liters is volume, so that must be V1. The pressure of the gas increases to 605 kilopascals. So kilopascals is pressure. So this is our new pressure. This is P2. As the temperature is raised to 125 degrees Celsius. So this must be our T2. What is the new volume? Well, so this new volume, V2, must be the one thing that we don't know. That's our unknown. So knowns. We know P1. We know T1. We know V1. We know P2. We know T2. Don't forget, those temperatures must be changed to kelvins. Anytime we work with temperature and gas, we have to think about it in terms of Kelvin. We know the unknown is V2, which is the number of liters. So now, since we know we're working with pressure, temperature, and volume, all three of them, we need to use the combined gas law. So again, we would write out our gas law, and then we would fill in the numbers, substitute in the numbers. So 155 is P1, 1 is V1, 298 is T1, 605 is P2, 398 is T2, but I don't know V2. And then it's a matter of simplifying. We would have to take 155 times 1 on the top here. We would have to divide that by 298. We'd have to get rid of the 398 on this side. Since it's being divided on this side, to move it over, we would have to multiply it. And then the 605 would need to be moved to the other side. And since it's being multiplied on this side, we would need to divide it on the other side. So go through and simplify all of that. And eventually we figured out that V2 equals 0.342 liters, right? We know it's liters because it was liters on V1. Therefore, V2 has to have the same units, right? The units have to be the same on each side. Like if P1 were in kilopascals and P2 were in atmospheres, this wouldn't work. We would have to make sure they're in the same units. So these are both liters, and that's our final answer, and we circle our final answer. Okay? So that's the combined gas law, which is really useful. Now, there is one variable that we have not covered yet in terms of gases, one left, and that is how much gas is in there. Okay? How much gas is in there can be measured in a couple of different ways, but the main way that we measure it in chemistry is we use something called the mole. Now, I realize we haven't talked about the unit, the mole, really at all yet. We're going to extensively eventually talk about it in a lot more detail. For right now, all you need to realize is the number of particles, right, can be measured by something called the mole. That's all you need to know about it. So if we introduce that into our equation, if we combine one more gas law, which we're not even going to talk about, it's called Avogadro's law, into it, we would get something called the ideal gas law. Okay? So Avogadro's law, just real quick, real simply, just means that if you have more and more gas, if the amount of gas increases, the pressure increases. So again, those are directly proportional to each other. So if we enter in the number of particles, that's what N stands for, the number of particles, then we have a super combined gas law, right? That has the extra variable we were missing from earlier in it. P1 times V1 over T1 times N1 equals P2 times V2 over T2 times N2. Or we can take out all of the 1s and 2s and we can look at it this way. The pressure times the volume equals the number of moles, the number of particles, times R, which is a constant, we'll talk about that in a second, times the temperature. So if we don't want to compare, let's say we don't have a first pressure and a second pressure and a first volume and a second volume. What if they just give us all the 1s and that's all we have? Then we'll have to put in a constant to make this work, and that's what R stands for. So again, let's write this out. So we have pressure. Normally in here, in this class, we're going to be working with it in kilopascals, although there are other pressure units we could use. Volume, which is almost always got to be in liters. So in this case, we have to have it in liters. N, which is the number of particles, and we measure that in moles. Okay, and the abbreviation for moles is MOL. R is that gas constant. It's just a number that we have to throw in here because we need it all to be equaled out. Okay, so the gas constant that we're going to use most often in here is 8.31. It, I believe, is listed on your equations and constants page, so you don't need to memorize it. And then finally, we have temperature, and we know that temperature, when we talk about gases. Always has to be in Kelvin. Okay? So this is called the ideal gas law, PV equals nRT. It's a really easy one to remember, although it is also on your equations and constants page. I do want to point out that if you decided to use atmospheres instead of kilopascals, let's say they give you a problem in which they give you atmospheres instead of kilopascals, you don't have to change atmospheres into kilopascals. You just have to use a different gas constant. Right? You would have to use this gas constant instead if we were using atmospheres. Okay? So that's the one thing that you have to be aware of when you're working with PV equals nRT, the ideal gas law. Right? You have to look at which unit of pressure are you using. The other units can't change. Okay? So don't forget, PV equals nRT. Really important. In fact, if I were to rank mathematical formulas in chemistry, this would be right up there, probably in the top 3 most important of all of the equations in all of chemistry. Okay, really important, gets used a lot. It's the most important out of all these gas laws that we've been talking about. So let's try to use it. When the temperature of a rigid hollow sphere containing 685 liters of helium gas is held to 621 Kelvin, the pressure of the gas is 1.89 times 10 to the third kilopascals. How many moles of helium does the sphere contain? So basically, it wants to know how much helium is in there. Remember, moles is just the amount of something, so it's the amount of helium. And we know the pressure, kilopascals. We know the temperature, 621 Kelvin. And we know the volume, 685 liters. Right? So let's write out what we know. The volume, 685 liters. The temperature, 621 Kelvin. The pressure, 1.89 times 10 to the third kilopascals. We know R. It didn't tell us in this problem, but we can already see where this problem is going. They gave us a volume, a temperature, a pressure, and they're going to ask us to solve for the number of moles, which is N. So we already have V, T, P, and we're going to be looking for N. Well, we can see that we're going to need an R at some point, right? Because PV equals nRT is the equation we're going to use. So what we're trying to solve for is the number of moles, that's N. So write out our equation, PV equals nRT, and then start substituting in your numbers. What's P? What's V? What's R? What's T? Let's fill in what we know. So P is 1.89 times 10 to the third. V is 685. N, I don't know what it is. I'm leaving it as N. R, we're using the 8.31 number because we're using kilopascals. So 8.31 is our R. And then T was that 621. So again, simplify. These two have to be multiplied by each other. So multiply those on your calculator. Simplify. These two have to be multiplied by each other. So multiply those two on your calculator. Then we have to move whatever this answer is over here. We have to move it on the other side. Since it's multiplied on this side, we have to divide it then to the other side. So again, I want you to pause for a minute, use your calculator, and figure out what this answer is going to be. And then we'll see, we can do a comparison to see how you did, okay? So go ahead and pause and do this on your calculator. All right, so hopefully you paused, you've gotten an answer. Should have looked like this. Now you may be thinking, well, my calculator didn't put it in scientific notation. That's all right, you don't have to. If this were not in scientific notation, it would be 251. So if you got an answer of 251 moles, then you're right. If you write it in scientific notation, it would be 2.51 times 10 to the second moles. Same number, okay? All right, so PV equals nRT. It's just an equation. Once they give us the numbers we have, we plug them into that equation, and we solve for the one thing we don't know. That's how this works. That's how all gas laws work, right? All right. This time, we're going to do something just a little bit different, okay? Just a little bit different. This one says a child's lungs can hold 2.2 liters. All right, so already we're thinking in our head, liters. Oh, that's a volume. How many grams of air do her lungs hold at a pressure of 102 kilopascals? Well, that's a pressure. And a body temperature of 37 degrees Celsius. Well, there's our temperature. All right, so we have a volume, we have a pressure, we have a temperature. Now, the weird thing about this problem is they're asking us for grams. Now, grams is mass. Wait a minute. There's no mass in PV equals nRT. Oh, but there is N, which is the amount there is. It's the number of moles. And so we have a way of converting grams to moles by using something called a molar mass. Again, we haven't gotten to talking about moles yet, but to be able to see the units, you can sort of get an idea what we're going to be doing here. If we know that air is 29 grams for every mole, if we can use PV equals nRT and solve for N, the number of moles, we could then convert that into grams using this conversion factor. That's all this is a conversion factor. So essentially, we're going to do the problem that we did up above, except that we're going to have one extra step to do at the end because we can't end our answer in moles. We're going to have to change it to grams because that's what this problem wanted us to do. Okay? So start by writing out your knowns and your unknowns. Again, pause the video, go do that, fill in your knowns and unknowns, and solve PV equals nRT for N. So get all the way to solving for moles, and then I'll show you how to do the last step. All right, so you've paused, you've figured out your answer. Here's what it should look like. Here are our knowns, right? We know V, the volume. We know P, the pressure. We know T, the temperature, which we had to convert into Kelvin. We know what R is. We were looking for N, which is the number of moles, but then we were going to have to change that into grams at some point. So PV equals nRT. Let's put in what we know. We know P. We know V. We know R. We know T. We just didn't know N. So if we solve for N, we get 8.71 times 10 to the negative second moles. Again, if you had written that out as a regular number, that would have been 0.0871. But that can't be our final answer because it's in moles and we need it to be in grams. So now we know that there's 29 grams for every mole. So if you take that answer times 29 grams per mole, that'll tell us how many grams that is. So in other words, we're multiplying that answer by 29. And we get 2.5 grams of air. So a little kid, when they breathe in, right, they're going to fill up their lungs with air. But remember, air is really light. So there's only a total of 2.5 grams worth of air total in a child's lungs when they breathe in. Okay? All right. One last thing about the ideal gas law. Okay? The reason why we call it the ideal gas law is we're going to assume that most gases are under high temperatures and low pressures. Like, for instance, again, in the room you're sitting in right now, the air pressure that you're sitting in is relatively high. It's about 101 kilopascals of pressure in the room you're sitting in right now. Okay. I'm sorry. Low pressure. I'm looking at high with temperatures and I'm thinking, okay, so low pressures. So the pressure in the room right now is 101 kilopascals. That's pretty low pressure, right? We could have a lot more high. We could have much higher pressure than that. We could have, 600 kilopascals or 1,000 kilopascals, but you're only at about 100 kilopascals in the room you're sitting in right now. Temperature in your room right now is somewhere around 298 Kelvin. Okay, 298 Kelvin. Now, for temperatures, that's a fairly high temperature. So we're assuming that under normal conditions, you have relatively low pressures of air, but relatively high temperatures. That's ideal. Gases act ideally in those situations. But other gases, you might have other situations where the gas might be at a really low temperature or a really high pressure, in which they would not be acting ideally anymore. So a quote-unquote real gas is a gas that has low temperatures and high pressures and doesn't exactly follow PV equals nRT anymore. So when we use the ideal gas equation, PV equals nRT, we're assuming that the gas is acting like a true real gas. It's not acting like a gas that's about to turn into a liquid or anything like that, okay? We're assuming it's acting like a gas. And so we use PV equals nRT under most conditions because even if it's a real gas, it's pretty close. It's a very good approximation, and it gives us the numbers that we need without having to get too complicated, okay? In fact, you can see in this graph here that if we look at real gases and ideal gases, okay, most gases don't act ideally unless they're really, really low pressures. And again, 101 kilopascals is a fairly low temperature. Look what happens to the way these kind of go off the rails as the pressure goes way up. As the pressure goes way up here, we get way far off of PV equals nRT. But most of the time, we're not working with really high pressures of gases. We're going to keep our pressures relatively low. And so as long as we're staying right around here, we're going to be all right. But if you were looking at this graph, let's answer a couple questions. Notice on the y-axis, we have PV over nRT. So what are the values of PV over nRT for an ideal gas at 20,000 and 60,000 kilopascals? Okay. So at 20,000, depends on what gas you're talking about. Are you talking about carbon dioxide or methane or hydrogen? Or okay, so we have a couple of different gases that we're working with here, right? And we can see that they might be as low as, what is this, about 0.35, or they might be as low as 0.7. Or they might be as high as all the way up here at hydrogen is a little over 1. Okay, so we get a little bit of a deviation from the ideal when their pressure goes way up. What variable is responsible for the differences between the two methane curves? Now notice we have two methane curves, right? We have this one that's sort of this pinky magenta color, and we have the other one that's sort of a purpley color. So this methane is at 0 degrees Celsius, and this methane is at 200 degrees Celsius. So we're comparing two methanes at different temperatures. So what's the variable responsible for the differences? The temperature. And finally, how does an increase in pressure affect the PV over nRT for real gases? Well, at first it might make it go down, but what's the general trend most of the time? Okay, most of the time it goes up, it increases as you get more and more pressure. So what do I want you to really remember about this? I want you to remember that ideal gases happen under high temperatures and low pressures, which is what we assume most of the time we're working with. Real gases could be at low temperatures and high pressures in which PV equals nRT is not exactly giving us the right numbers, but it's close enough. Okay? And then again, there's a couple laws that we have left, and we'll talk about that in the last part.